Yes, exactly.
Okay. So that is what I'm going to talk about. First off, talk about the model, which came from Niels Bohr. He was a Danish physicist and chemist. He developed this atomic model, and he assumed the energy states were just in integers like 1, 2, 3, just because of like the energies, 1, 2, and then 3. And so he assumed that everything was integer, but I kind of went a little bit further and fractionalized that, so like non-integer states. I'm sure he would have, but MATLAB didn't exist back then in the 20s. So I have a few movies. This is just the angular momentum with the different amount of nodes. So this is 1.5, so this would have been like 1.5. Like, play. So as you can see, it's kind of not symmetrical, and there's a lot of noise, and it looks kind of, I don't know, not good. And here's 2.45. Same. It kind of started to take shape a little bit. Still a lot of noise, and it's bigger too. Here's 2.67. Kind of a lot of the same. Starting to get a little bit more better, I guess. I did positive and negative for 2.9, and this is showing it's really starting to take shape. So this is the positive, and as you can see, it kind of rotates clockwise. And then here's the negative, and it's the same thing, but it's kind of going counterclockwise. So that showed like the negative effect on it. And then finally, here's the integer value of 3. So as you can see, it's really symmetrical and pretty, and kind of matches the theoretical a lot better. Not really any noise. So what I took away from this is the closer, the more symmetrical it is, and the less noise, and then the negative value will change the direction of the rotation. And then along with that, the code produced the transfer potential of an electron. So there's huge spikes, like this is really, really, really small. Like it's basically 0. So this is kind of indicating stability. So right at the integers at 3 and 4, there's huge spikes of basically the transfer being 0. And then also I noticed, so the increase in nodes also increases the size, the radius. So another thing was like, this is 4.5 and this is 1.5. So like, as it gets bigger, it also gets more stable, along with being closer to the integer value. Yeah, it's kind of what we just kind of talked about that. And then another thing that I observed was the eigenenergy states for each amount of nodes. So this one, it just is 1.5, so the ground state is here, and then this is like the first excited. Right? And then here's 2.45. As you can see, they're coming closer. And then 2.67. And then 3.01. It just keeps getting closer and closer and closer. So from that, we observed the more nodes, lower it gets, and the ground state is the same. It's the lowest energy. It's open for questions.
Okay, let's thank Michael. And what are the questions?
So, what is the main kind of idea of Bohr model, by the way?
It's just projecting. I'll go to the picture.
And what is main postulates maybe he was making?
That the stability at these different levels, it just kind of naturally goes to that because it's the lowest energy here, I believe.
Then I'm not really sure what was your reason to take in not, like you were taking, I don't know what you start with, don't remember, but you're taking like 1.5, 2.9, 2.8, up to 3, right?
Yeah.
And you call it noise, but what exactly was the purpose taking the not integer number of nodes?
Okay, so just to observe
for the waves, right?
Sorry. Yeah. So it's just taking like a wave packet and taking it into like a radial kind of view. so like kind of polarizing it, or the coordinates. So it's just kind of showing that that's how many cycles goes through. So it has to be kind of even. What was the idea is it has to be even, so it like matches up in the end. So then it's like a smooth transition as it goes around the circle. Does that kind of answer the question?
Is it standing wave?
Yeah, and then convert it.
But my understanding is that to get the quantized energy, and the main postulate of Bohr, and actually the main idea of the Bohr model, is that it provides the quantized energy for electronic levels. That energy is taken, this number, corresponding to N1, N2, N3, not in between. And for this, you need to have actually the even number, not even how it calls, the total integer number. The integer number of wavelengths.
Yeah.
And the nodes actually kind of also should be the integer number, not in between.
Yeah, that was kind of what I was looking at, was the fractionalization of that. So like what the behavior of that was.
Oh, so actually
So-
your goal was to show not quantized behavior,
Yeah.
right?
Yeah.
Kind of you were comparing the case when it's pure
Mhm.
quantum case as electron behave in an atom versus something not really quantum in between, and this is what you call noise.
Yeah. Yep. The nodes is the width, like how many wavelengths. Yeah.
Okay.
So yeah. So it kind of proved like everything's a lot more stable when it's integer. So,
If you have integer number
Yeah.
of nodes.
yes, correct.
Okay.
More questions? Please.
So if you're, say, in 1.5, can you think of that as being like a superposition of 1 and 2, or is that not the right way to think about it?
That's the way I kind of thought of it. I don't know. I think.
Maybe
Imagine
more.
so.
Superposition of several things. If there are no more questions, I thank Michael once again. And the next presenter is Gage Miller, who will continue on the rotational motion and some aspects of it.